Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at the Gauss Seidel method. So in this topic, we are going to describe a small change to the Jacobi method. Specifically, given that we are calculating the entries of the next vector one at a time, why not use the previously calculated next entries while calculating subsequent next entries? We're going to observe that this small change results in faster convergence, and it guarantees convergence for another class of matrices, and most importantly, it requires no additional work. You will recall that the Jacobi method approximates a solution to A times U is equal to a target vector V by iterating the following algorithm. The next approximation is the inverse of the diagonal entries of the matrix A times the target vector minus the off-diagonal entries of A times the previous approximation of U. Normally, you think of matrix operations like this as calculating on the entire vector one at a time, in its entirety. Again, that's how you were introduced to the concept of matrix vector operations in linear algebra. However, you'll remember that we can calculate each entry of a vector one at a time. Now, Gauss and Seidel realized that when we are calculating the next approximation, then as we go through it, the previous values that we've calculated are already closer to the actual solution. So why continue to use the old values when we already have values that are theoretically actually closer to the target? So basically, what we're going to do is update the vector as opposed to creating a completely new vector just from the old vector. So the next approximation is going to be initialized with the current approximation of the solution. What we will then do is, for the next approximation, we will update each of the entries one at a time. So basically, we will start with the first entry, and then the second, and so on and so forth. And for each of the ith entries of the next approximation, we will replace the ith entry with 1 over the diagonal entry of the matrix A times the ith entry of the target vector minus the ith row of the off-diagonal entries of the matrix A times the current vector U sub k plus 1. What's nice here is that when, for example, we are calculating the third entry of the updated vector, the first two entries have already been updated and are now being used to calculate the third entry, rather than using the first two entries of the previous vector. So visually speaking, this is what's actually occurring when we're solving or approximating a solution to this system of linear equations using the Jacobi method. We have the matrices, the matrix of diagonal entries and off-diagonal entries, and when we have U sub k, we simply calculate the in this case, the 6 entries of the next approximation, one at a time, and thus we have found the next approximation to the system of linear equations. Visually speaking, let's see what happens with Gauss Seidel. With Gauss Seidel, we assign the next entry U sub k plus 1 the entries in the previous value or vector U sub k. However, we're going to update this vector as we proceed. So rather than calculating all of the entries, what happens is as follows. We first use the right-hand side to calculate the first entry. But this value now also appears in the right-hand side. So when we calculate the second entry, we're using the updated entry in the first location. So then we calculate that, but that now also appears on the right-hand side. So when we calculate the third, the first two are already pushed towards the solution. So the entire vector is closer to the solution than we were when we were calculating the first entry. And so on and so forth. At this point, when we're calculating the last entry, the first 5 entries have already been updated. So it's as if we're getting a further push towards the actual solution. And now we can compare whether or not uk plus 1 is sufficiently close to u sub k to see whether or not our iteration should be halted. Now the Gauss Seidel method continues to converge if the matrix is strictly diagonally dominant. As a bonus, it actually speeds up the convergence actually quite significantly. Unlike the Jacobi method, however, the Gauss Seidel method is also guaranteed to converge if, for example, the matrix is symmetric and positive definite, a class of matrices that is very common in engineering. And as you know, all the eigenvalues of a symmetric matrix are real. A positive definite symmetric matrix is one where all the eigenvalues are strictly greater than 0. That is, they are all positive. Basically, what this means is that if you map any vector under such a symmetric positive definite matrix, the image will still point in the same general direction of the original vector. That is, the two vectors will not be, the image will not be orthogonal or point in the opposite direction. So again, such a matrix has all positive eigenvalues. Now previously we showed you the Matlab code for implementing the Jacobi method. Here is the Matlab code for implementing the Gauss Seidel method. What's the difference? Well, just one component of one line. Previously, when we were calculating the next vector, we always used the previous vector. Now, that was the previous vector. Now we are using the current vector, which is being updated one at a time. Consequently, if j is less than I, we are now using updated values, whereas if j is greater than I, we are still using the old values. This basically gives us a push in the correct direction. Following this topic, you now have an understanding of the Gauss Seidel method. You understand that we can use more recent vector entries when we are calculating subsequent vector entries for the next iteration. You understand that this allows for faster convergence, and you are aware that this works on a greater range of matrices at no additional cost, which is nice. There's no additional floating point operations required. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!